Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at mathematical induction, a very useful tool for proving that something is true for natural numbers n. So you want to prove that something is true for n equals 1 and n equals 2 and n equals 3 and n equals 4. This is an extremely useful process. So to do this, you follow 3 steps, the first 2 of which are easy. Firstly, you prove true for the base case. Generally, you will be asked to prove something's true for all integers greater than or equal to 1. In that case, you would prove that it's true for n equals 1. It won't always be n equals 1. It could be n equals 2, n equals 0, whatever, but you prove true for the lowest value of n. That's generally pretty easy. The second step, the inductive hypothesis, is also really easy. You just write a statement here. You assume that what you're trying to prove is true for n equals k. The third step is where all the work is done, the inductive step. So you need to prove that if your assumption that you wrote in step 2 is true, then it's true for n equals k plus 1. So the idea here is you prove it true for, say, n equals 1. Then you're proving in these 2 steps that if it's true for n equals 1, it's true for n equals 2. If it's true for n equals 2, it must be true for n equals 3. If it's true for n equals 3, it must be true for n equals 4. So in this way, you've proved it's true for all of the integers starting from your base case. All right, let's look at an example. So we're going to prove that 2 to the power of 4n plus 1 plus 3 is divisible by 5 for all integers n is greater than or equal to 1. So the first step here is the base case. We prove true for the lowest value of n. Here the lowest value that n can take is 1. So all we do is go to our statement here and substitute in n for 1. So 2 to the power of 4 times 1 plus 1, 2 to the power of 5 is 32, plus 3 is 35. Now clearly 5 goes into 35. 35 is divisible by 5. It is true. So we have done step 1. So step 2 is the inductive hypothesis. So we assume that the statement we're trying to prove is true for n equals k. So we assume that if I substitute n for k, that this is divisible by 5. I'm just going to write it like this. This says 2 to the power of 4k plus 1 plus 3 is divisible by 5. So we haven't actually done any thinking yet. Now we go to the inductive step. So now what we need to do is prove that it's true when n equals k plus 1. So we're going to take our assumption here and basically change n to k plus 1. So here, if I change n to k plus 1, I get 2 to the power of 4. Now I need to put it in brackets here. K plus 1 plus 1 plus 3. That's what I have. So let's expand the brackets. I get 2 to the power of 4k plus 5. So that's what I get when I expand this bracket and simplify, plus 3. I need to show that this is also divisible by 5. But I can use my assumption here. So note that this here, using our index laws, is 2 to the power of 4k plus 1 times by 2 to the power of 4. Because when you multiply bases, you keep the same base and add the powers, 1 plus 4 being 5. Okay, so how does that help us? So this is 16 times that. So I can write it as 15 times 2 to the power of 4k plus 1 plus another lot of 2 to the power of 4k plus 1, because 15 lots of something plus 1 lot of something equals 16 lots of something. So what I have is this. this here is clearly divisible by 5 because it's divisible by 15. If you divide this by 5, you get 3 times this. You get an integer. So that's clearly divisible by 5. Now this here is divisible by 5 because of our inductive hypothesis. We assumed that this was true. So if this is true, if this is divisible by 5, then I have a number divisible by 5 plus a number divisible by 5. I have the sum of two numbers divisible by 5. So if this is true, then this is also divisible by 5. If this statement is true for n equals k, it is true for n equals k plus 1. So because it's true for n equals 1, it's true for n equals 2. Because it's true for n equals 2, it's true for n equals 3, and so on. So at the end here, you just need to write a statement here about why that's divisible by 5. So I'll just call this 5p since it was divisible by 5. Here p is an integer, and then I can factorize this as 5 times an integer. So I've proved what I wanted to. Let's look now at one more example. So we're going to use mathematical induction to prove this formula. This is the formula for geometric series. Note this notation means for all n in positive integers. So here we're going to start at n is equal to 1. So the base case, n equals 1. Remember, n is the number of terms in geometric sequences like this. So if n equals 1, we just get on the right hand side a times r to the power of 1 minus 1 over r minus 1. Now obviously these two cancel out and you just get a. So we have proved that this formula holds, this formula works for the base case n equals 1. So our second step is our inductive hypothesis. We assume that it's true for n equals k. We assume that this is true if I substitute everywhere you see an n for a k. So now we're up to the inductive step, which is where all the work gets done. We need to show that it is also true if n equals k plus 1. So what I'm going to do is go through here and replace the n's with a k plus 1. So if I replace n with k plus 1, there's now this one extra term here. The number of terms is k plus 1, whereas there were k terms in this one. So by the inductive hypothesis, this thing here is equal to a r to the k minus 1 over r minus 1. So that's all of these terms here, but then we need to add this onto the other side so that the equations are balanced. So what I basically need to do is rearrange this so it looks exactly like this, except there's a k plus 1 here. So what I'm going to do is I am going to make this all one fraction by making this a fraction timesing top and bottom by r minus 1. So now I'm just going to expand the brackets at the top, a times r to the power of k plus 1. So now I go r times a r to the power of k. It will just be a r to the power of k plus 1. And then minus 1 times a r to the power of k. Alright, now we can cancel out on the top. This minus this is just 0. We can also factorize the top because here there is a common factor of a. So taking out the common factor of a, we're just left with r to the k plus 1 minus 1 over r minus 1. We're actually done. We have shown that this formula still holds true if you add another term. We have shown that this formula still holds, this original formula holds if n equals k plus 1, because you can see I've just replaced n with k plus 1. So again, we have shown that because it's true when n equals 1, and because if it's true for n equals k, it's true for n equals k plus 1, we've shown it must be true for n equals 2, for n equals 3, for n equals 4, and so on, for all positive integer values of n. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.